Continuing on with the Chem 112 Chapter 9 lecture series, we're going to continue on with our lecture to discuss now elimination reactions and the regiochemistry of elimination reactions. So what is an elimination reaction? So elimination is the loss of a leaving group and a proton to yield an alkene. Elimination of the leaving group can occur at high temperatures or in the presence of strong base. So here our base is going to pull off a hydrogen. We form a carbon-carbon double bond with concomitant loss of our leaving group. One rule that helps us predict the regiochemical outcome of elimination reactions is Zaitsev's rule. In elimination reactions, the more highly substituted alkene product predominates. A rephrasing of Zaitsev's rule is that the most stable alkene product predominates. So for example, this di-substituted alkene is preferred to form over a monosubstituted alkene. Here's a general ranking in terms of relative alkene stability. With among di-substituted alkenes, the trans alkene is preferred over the cis alkene, in part because the cis alkene has some steric hindrance and strain. In general, the more substituted alkene product is going to prefer, with some exceptions. One thing to note is that conjugated alkenes are especially stable, and so their elimination reactions are quite fast. Additionally, elimination to generate an aromatic ring is very fast. So anytime you have elimination to generate a benzene ring, which is aromatic because it has 6 pi electrons, these reactions will be very fast. One of the major classes of elimination reaction is the E2 reaction. E for elimination, 2 for bimolecular. The E2 reaction follows second-order kinetics, where both the alkyl halide and the base take part in the rate-limiting step. In the E2 reaction involves a concerted abstraction of an adjacent proton by a strong base and departure of the leaving group. So this rate-limiting step is bimolecular. Your base abstracts a proton, you form your carbon-carbon bond, and you lose the leaving group in the same step. This is what the transition state looks like for the E2 reaction, where you're breaking the carbon-hydrogen bond, forming a carbon-carbon double bond, and breaking the carbon-leaving group bond. One thing to note is that the E2 reaction is very particular about the relative arrangement of the hydrogen and leaving group. The E2 reaction specifically requires the hydrogen and leaving group to be anti-periplanar to one another. So in this case, we pull off this hydrogen, we form our carbon-carbon double bond, and we lose our leaving group. The E2 reaction, as we'll see as we continue on with this discussion, is a stereospecific reaction and requires the hydrogen and leaving group to be anti-periplanar to one another. Just to make sure we're familiar with the E2 reaction, let's practice drawing a mechanism for the following E2 reaction, and let's predict the products. So in this case, we have our leaving group, which is bromine. Our base, which is methoxide, is going to pull off a proton. And we lose the leaving group concomitantly to form an alkene. Okay, so this is the basic E2 reaction mechanism. Let's talk a little bit about the kinetics and reaction coordinate for the E2 reaction. The E2 reaction rate law is second order and dependent on the substrate and base concentrations. This supports the reaction mechanism, where in the rate limiting step, there is a concerted abstraction of a proton and loss of the leaving group to form the alkene. The rate limiting step is bimolecular. In terms of the E2 reaction coordinate, the E2 reaction is the reaction with a single transition state. The rate limiting step is bimolecular. As the substrate becomes more substituted, the rate of E2 reaction increases, with tertiary substrates having the fastest rate of E2 reaction. This makes sense because the transition state has alkene-like character. And as a result, the alkene-like transition state is stabilized by increasing substitution. The more stable your transition state, because your alkene that you're forming is going to be more substituted, the lower the activation energy for the E2 reaction. That's why the more substituted your substrate, the faster the rate of E2 reaction. Now, let's talk a little bit about effects of reaction conditions on the E2 reaction coordinate. Increasing substitution results in a faster rate of reaction. Why? The more stable the alkene and the alkene-like transition state, the lower the activation energy. So if we compare a primary and secondary substrate, the E2 substrate, the E2 reaction will be faster for the secondary substrate. So if we compare a primary and secondary substrate, the secondary substrate, the more substituted substrate, has the faster rate of E2 reaction. In terms of leaving group effects, the better the leaving group, the faster the rate of E2 reaction. So if we have a choice between a hydroxide and an iodide leaving group, the alkyl iodide substrate will have the faster rate of E2 reaction because it has the better leaving group. In terms of solvent effects, polar protic solvents stabilize the base and risk protonating the base, giving a slower reaction rate. So generally, we prefer to use polar aprotic solvents because they give a faster E2 reaction. Because we're not risking stabilizing or protonating the base and slowing down the reaction. Polar aprotic solvents are preferred for fast E2 reactions. So if we have a choice between these two solvents, what solvent would best facilitate a fast E2 reaction? We have a choice between a protic solvent and an aprotic solvent. I'm going to pick the polar aprotic solvent because those solvents generally yield faster E2 reactions. They're not interfering with and stabilizing our base. They're not hindering and slowing our reaction down. Let's talk next about the stereospecificity of the E2 reaction. The E2 reaction is stereospecific in that the E2 reaction requires the hydrogen leaving group be anti-periplanar or transdiaxial to one another. The anti-periplanar conformation positions the carbon-hydrogen and carbon-leaving group bonds for efficient orbital overlap. So if our carbon-hydrogen bond and carbon-leaving group bonds are anti-periplanar, we see we have great overlap with each of the bonds' sigma star orbitals. This makes it very easy for us to push electron density into the sigma star orbital and break the carbon-leaving group bond. So the E2 reaction requires an anti-periplanar position of the carbon-hydrogen and carbon-leaving group bond. Now, when it comes to predicting the products of E2 reaction, Elimination often requires bond rotation so that the beta hydrogen and leaving group are anti-periplanar. So for example, in this case, the hydrogen and bromine are anti-periplanar, so we have efficient elimination. From a Newman projection view, we see that when the hydrogen and the leaving group are anti-periplanar, the two phenyl groups end up on the same side, and the hydrogen and bromine end up on the same side of the alkene. So these two phenyl groups are cis to one another. So it's really important that when we think about elimination reactions for acyclic systems, you need to draw the Newman projection, set up the hydrogen and bromine in an anti-periplanar arrangement, and from there you can identify what substituents are going to be cis to one another in the final alkene. As you can see, the phenyl groups are on the same side in the Newman projection with the hydrogen and bromine anti-periplanar, so the two phenyl groups are cis. When we get to cyclic systems, things get a little bit more interesting. In cyclic systems, elimination requires the beta hydrogen and leaving group to be trans-diaxial. So in this case, we have two possible hydrogens for elimination. These hydrogens are trans-diaxial to the leaving group, and thus the base can pull off and eliminate one of these trans-diaxial hydrogens. Importantly, your molecule must adopt the conformation that places the chlorine axial and trans-diaxial to a proton. If there's no trans-diaxial hydrogen, or if the chlorine, the leaving group, is not in an axial position, you will not see an E2 reaction for that conformation. Now, why is this important? Well, let's do some case studies on stereospecific E2 reactions. So treatment of the following compound with a 1R, 2R configuration gives the most substituted E-alkene product. So let's show why that is. So in this case, taking our original structure, we can draw a Newman projection looking this way down our carbon-carbon bond. In this case, everything with a wedge ends up on the right, everything with a dash ends up on the left. This group is pointing up, this group is pointing down, and this maps on to our Newman projection. Now, what we're going to do is we're going to look and see if there's a hydrogen anti-periplanar to this bromine, which there is. We can also identify it as this hydrogen here, which is anti-periplanar to our bromine. Redrawing this Newman projection, just tilting the whole thing roughly 60 degrees, we see that the bromine and hydrogen are anti-periplanar. So when the base pulls off a proton and we lose our leaving group, we see in our final alkene, the methyl and ethyl group are going to be on the same side, and the hydrogen and ethyl group are going to be on the same side. So we get the E-alkene product. So we start with the defined reactant stereochemistry, and we get out a defined product stereochemistry. So we get defined regiochemistry, we get the most substituted alkene, and we get a defined stereochemistry. You can also draw this shortcut where the base pulls off a proton, you lose the leaving group, and as you can see, in this case, when that occurs, the methyl and ethyl group are cis to one another. I would strongly recommend using the Newman projection method because it may not always be the case that your hydrogen and bromine are perfectly lined up for E2 reaction, are perfectly set up anti-periplanar to one another. Now, with this example in mind, I'd like you to draw a Newman projection, mechanism, and product for the E2 reaction of the 1s2r isomer. So the only thing that's changed is that this bromine is now dashed. So take a few moments, pause the video, and work through this example, and then we'll discuss. So first things first, I'm going to draw out my implied hydrogens. So I'm going to draw a Newman projection looking down this carbon-carbon bond. Everything with a dash ends up on the left. So the bromine has a dash, the hydrogen has a dash. Everything with a wedge ends up on the right. So we have the hydrogen and a methyl group. We have the ethyl group pointing down in the front and an ethyl group pointing up in the back. From here now, we're going to rotate our molecule such that this bromine and this hydrogen are separated by 180 degrees. They're anti-periplanar to one another. So if I have my bromine, hydrogen, and ethyl group, what I'm going to do is I'm going to rotate this bond 120 degrees such that the hydrogen is in the place of the methyl group. So the hydrogen's here now, the methyl group is here, and the ethyl group is here. We just rotated our carbon-carbon bond 120 degrees. From here, the bromine and hydrogen are anti-periplanar, so we can eliminate our leaving group. Thus, in this case, the two ethyl groups are cis to one another. So in our final alkene, the two ethyl groups are cis, and the hydrogen and methyl group is cis. This gives us the Z-alkene product. As you can see, if we change the reactant stereochemistry, our product stereochemistry changes. The E2 reaction is stereospecific and regioselective. So pay special attention to the reactant stereochemistry because the E2 reaction requires an anti-periplanar arrangement of the hydrogen and leaving group. So we've done an example, a case study for the acyclic systems. Let's look at some examples of regioselectivity for the E2 reaction, and let's talk about ways that we can get regioselectivity via reagent control. If there are multiple possible anti-periplanar hydrogens, product mixtures are observed. E2 reactions are generally selective for the E-alkene and the most substituted alkene. So we're going to prefer to make the E-alkene over the Z-alkene because the E-alkene, you avoid this steric interaction if you have your large, bulky groups on the alkene cis to one another. This can also be reasoned by looking at the Newman projection, noting that the conformation required for elimination to yield the E-alkene is lower in energy as it lacks these destabilizing gauche interactions. So as you can see, to make the Z-alkene, this conformation is strained, while to make the E-alkene, the conformation is less strained. So if you have a choice, you're going to make the most substituted E, which is the trans alkene. So I'd like you to take a few moments now and try to predict the product of this reaction and draw a mechanism. So pause the video, work through this example, and then we'll discuss. So in this case, we have two hydrogens that after bond rotation can be placed anti-periplanar. So if we pull off the hydrogen, and that in turn will yield the elimination product, we will prefer to generate the E alkene as the major product. And we will also get a little bit of the Z alkene as the minor product. Generally, E2 reactions favor generation of the most substituted alkene and the E, in other words, the trans alkene. Let's keep going now, and let's talk about the E2 reactions of cyclic systems and examples of regiospecific E2 reactions. So, as I have discussed, the E2 reaction requires the abstracted proton and leaving group to be anti-periplanar. For cyclic systems, this requires the hydrogen and leaving group to be transdiaxial. So for cyclic systems, E2 reactions can be regiospecific if only one hydrogen can be transdiaxial. For example, in the following molecule, only one of the adjacent hydrogens is transdiaxial to your carbon leaving group bond. So in this case, only one of the hydrogens can be eliminated and participate in an E2 reaction, and thus you get a single regioisomer. Note, this single regioisomer may not be the most substituted alkene. So it's always important, because the E2 requires a transdiaxial arrangement between their cyclic substituents, you can only eliminate the hydrogen that is transdiaxial to your leaving group. The E2 reaction is regiospecific in many cyclic cases. Now, of course, if there are multiple transdiaxial hydrogens, then of course the more substituted alkene is favored. In this case, there are two transdiaxial hydrogens, and we're going to prefer to eliminate the hydrogen that would yield the most substituted alkene. So with all this in mind, let's take a look at the following example. Let's try to predict the product from this reaction. I'd want you to draw the chair conformation that reacts, and I'd like you to draw a mechanism for the following reaction. Anytime you approach the E2 reaction of a cyclic system, you are going to need to draw the chair conformations out. It is not an optional step in this process. Okay, so let's discuss. So first and foremost, let's draw the chair conformation. So here the bromine is wedge, so it's axial up. On the adjacent position, the methyl group is dashed, so it's pointing down. And then we have two hydrogens like so. In this case, there's only one transdiaxial hydrogen to the bromine, and thus the base will selectively attack and eliminate that hydrogen, and that in turn would yield the elimination product that looks like this. Viewing it another way, this hydrogen is eliminated, we lose our leaving group, and we selectively get the following product. So again, the E2 reaction is regiospecific in many cyclic systems, and you can only eliminate the hydrogen that is transdiaxial in relation to your leaving group. Okay, let's talk a little bit about the kinetics for E2 reactions of cyclic systems. The E2 reaction requires the hydrogen and leaving group to be transdiaxial. Thus, the molecule with the lowest energy conformation containing the required transdiaxial hydrogen and leaving group will generally react faster via E2 reaction. For example, if we compare these two stereoisomers, in this case these two diastereomers, in one diastereomer, in order to place the bromine axial, you have to place the methyl group axial. which means we have a higher energy chair conformation. Because this molecule has a higher energy chair conformation than its diastereomer, where when the bromine is placed axial, the methyl group is equatorial. The bottom molecule, the bottom stereoisomer, will have the faster rate of E2 reaction because it's easier to access the chair conformation with the required transdiaxial arrangement of the hydrogen and leaving group. It's the exact same logic that we used when we discussed the SN2 reactions of cyclic systems. So with that in mind, let's try to apply what we've learned, and I'd like you to tell me which of the following compounds will have a faster rate of E2 reaction, and I'd like you to draw the products. So pause the video, take a few moments to work through this example, and then we'll discuss. Okay, so first and foremost, let's draw the chair conformation. So in this case, my chlorine is wedged, so it's going to be axial up. The isopropyl group is wedged, so it's going to be equatorial up. We have the two hydrogens. And then finally, the methyl group is axial down. Looking at the alternative chair conformation, the chlorine would be equatorial. This group would be, well, we don't even have to consider it because this chair conformation already has the leaving group in the axial position. Let's look at our second molecule now. So in this case, the chlorine is equatorial down. We have the isopropyl group and methyl in the same position. Let's look at a chair flip now because we need the chlorine to be axial in order for anything to happen. Here, if the chlorine is axial down, the isopropyl group is axial up, and the methyl group is equatorial down. Okay. So the second molecule, even though it has the chlorine axial, pays a huge penalty for this because we end up having to place this large isopropyl group in the axial position. As a result, this conformation is high energy and difficult to access. This in turn means this compound will have a slow E2 reaction. By comparison, the compound on the left only plays a minor penalty, placing the methyl group in the axial position, and so this conformation is easy to access as it's low energy, and thus the elimination reaction occurs readily. Well, that's not the proton that's going to be eliminated in this case, because even though we have a choice of two transdiaxial hydrogens, one of them will give a more substituted product. So the base is going to come in and pull off this proton, and we observe elimination to generate our highly substituted alkene. By comparison, if elimination occurs in this case, there's only one proton that can be pulled off, and that in turn yields the following product. So we're pulling off this proton here, which yields the following product. So, two takeaways. You really have to check the chair conformation and see which chair conformation is more easy to access. The E2 reaction is stereospecific, and the proton that gets eliminated is the proton transdiaxial to your leaving group. Okay, so we discussed the E2 reaction in the context of cyclic and acyclic systems. Let's talk about some reagent control. So let's talk about the use of bulky bases to get anti-Zaitsev regioselective E2 reactions. So bulky bases result in selectivity for the least substituted alkene. So if we compare ethoxide to tert butoxide is bulky, and as such, we primarily get the least substituted alkene. Examples of bulky bases include diisopropylamine and diisopropylamide, tert butoxide, and triethylamine. To explain why this occurs, the approach of the bulky base to generate the most substituted and lowest energy alkene would result in a high energy transition state as a result of steric clash. Because when you use a bulky base, the base is sterically crowded. If it tries to approach the hydrogen that would yield the most substituted alkene, it runs into a lot of steric hindrance. As a result, when you have a bulky base, it prefers to abstract the least hindered hydrogen to yield the least substituted anti-Zaitsev alkene. So let's try to predict the products from the following reactions. I'll do the first one. So we have many protons that we could pull off here. In terms of the least hindered protons, these are going to be the protons attached to the methyl group, and that in turn yields the least substituted alkene. This is a very useful method to generate what are known as exocyclic alkenes, which are otherwise pretty difficult to access. With that example in mind, I'd like you to try to predict the product of the following reaction. So pause the video, work through this example, and then we'll discuss. Okay, so in this case, we have a choice. We can either pull off this highly hindered proton or these more accessible protons. Because we're dealing with a bulky base of tert butoxide, we're going to pull off the least hindered, most readily accessible protons to in turn yield the least substituted alkene. So whenever you use a bulky base, you get the least substituted alkene product. Wonderful. Let's now talk about a variant elimination reaction known as the E1CB reaction. The E1CB reaction is a unimolecular conjugate base elimination reaction. In the E1CB mechanism, an acidic beta proton is deprotonated by the base to yield a stabilized anion, and then you have elimination of the leaving group to yield the alkene. So in essence, you generally need to have your leaving group, and then on the carbon adjacent to your leaving group, you need to have a proton and an electron withdrawing group, such as a nitro group, a ketone, etc. The reason why you need that electron withdrawing group is because this first deprotonation step can be difficult without an electron withdrawing group. Once you deprotonate and generate your anion, that anion then eliminates and kicks out the leaving group to generate an alkene product. The second step, elimination, is the rate limiting step for the E1CB reaction. In terms of the reaction coordinate, there are two steps, with elimination of the leaving group being the rate limiting step. One thing I'd like you to note is that as we can see in this substrate, we have multiple electron withdrawing groups on the carbon with the proton that's going to be abstracted to ensure that our anion is sufficiently easy to generate and it's stabilized. So let's look at some examples of the E1CB reaction. So E1CB reactions are accelerated if the leaving group is good and the beta proton is acidic. So one example is E1CB elimination to make aldol products. So in this case, you get deprotonation. This generates a stabilized anion, which then kicks down to eliminate your leaving group. Another example of the E1CB reaction that we've seen before is the elimination of vinyl halides. In this case, you have deprotonation. This anion then eliminates where you kick out your leaving group. To make sure we're comfortable just drawing E1CB reactions, let's try to predict the products of the following reaction and draw a mechanism for this reaction. I'll give you a hint. We have this electron withdrawing group right here. So pause the video, take a few moments to work through this example, and then we'll discuss. So in this case, our base is going to pull off a proton. This yields a stabilized anion. And even though this equilibrium pretty massively favors the reactants, once you get this anion, it's very easy to eliminate and kick out your leaving group to generate this conjugated alkene. And once you kick out the leaving group, the E1CB reaction really doesn't go in the reverse direction very easily. Okay, let's now talk about the other major class of elimination reaction, which is the E1 reaction. E1 indicating it's a unimolecular elimination reaction. The E1 reaction is a unimolecular elimination reaction that proceeds via carbocation intermediate. In the mechanism, you first lose the leaving group to make a carbocation, and then you have elimination of a proton to generate the alkene. One thing I would like you to note is that the E1 reaction is often observed as a competing reaction with the SN1 reaction, as the first step, carbocation formation, is identical and rate limiting for both reactions. As discussed in prior chapters, to favor elimination via the E1 pathway, you need to use higher temperatures and low nucleophile concentrations. So as we increase the temperature, you'll observe more and more elimination product. So let's practice drawing the mechanism for the E1 reaction. So let's take a look at this substrate. Let's pause the video, work through this example, and then we'll discuss. So first step in the E1 reaction, you lose the leaving group to generate a carbocation. From here, your nucleophile, rather than attacking, is going to abstract a hydrogen. Why are we abstracting this hydrogen? We'll abstract the hydrogen that yields the most substituted alkene, which is the following alkene product. This is our major product, and you get a vanishingly small amount of this product, which is minor, which I'll say very minor. So the E1 reaction, You form a carbocation via loss of the leaving group, and then you pull off a proton to eliminate a proton and generate your alkene. Now, in terms of the E1 reaction, let's talk about the kinetics and reaction coordinate. The E1 reaction rate only depends on the concentration of substrate. This supports the mechanism in which carbocation formation is the rate-limiting step. In terms of the reaction coordinate, the E1 reaction shares a lot of similarities with the SN1 reaction in that the first step, carbocation formation, is the rate-limiting step, and both the E1 and SN1 reactions go through a carbocation intermediate. So again, the first step is rate-limiting. Now, why is this important? Well, the E1 reaction is very sensitive to substrate effects. The E1 and SN1 reaction have the same rate-limiting step, so the reactions have similar properties. The more stable the carbocation formed, the faster the rate of E1 reaction, with tertiary substrates being much faster than primary and secondary. As a reminder, primary carbocations do not form. As an additional warning, fluoride is not a good leaving group. So please do not propose substitution and elimination of fluoride under normal reaction conditions. Fluoride requires special conditions to force it to leave. So looking at these two substrates, if we have a tertiary and secondary substrate, the tertiary substrate will have the faster E1 reaction. Now, because carbocation formation is rate limiting, the rate of E1 reaction increases if the substrate has a good leaving group. For example, the alkyl bromide will have a faster rate of E1 reaction because bromine is an actually good leaving group. F minus does not leave in most cases. If we compare hydroxide versus a tosylate, remembering that a tosylate or a tosyl group looks like this, the tosyl group is a great leaving group, and so the tosylate will have the faster rate of E1 reaction. It's easier to get to that carbocation. Just like SN1 reactions, the E1 reaction is facilitated and accelerated by polar protic solvents, as polar protic solvents stabilize the carbocation and facilitate carbocation formation. So if we have a choice between these two solvents, which of these solvents would give a faster rate of E1 reaction? We have a choice between a protic solvent and an aprotic solvent, and as we discussed, polar protic solvents yield faster E1 reactions because they stabilize the carbocation and lower the activation barrier. Now, we have to address what is the elephant in the room, which is the fact that the E1 and SN1 reaction are competing reactions. The E1 reaction competes with the SN1 reaction as the first step carbocation formation is identical for both reactions. Further, it's an identical rate limiting step. This is problematic because once the carbocation is formed, both E1 and SN1 reactions occur to yield a mixture of products. So as you can see, because the first step is rate limiting, once you get your carbocation, you don't have really any good control over your product selectivity because you aren't able to govern product selectivity through the rate limiting step. So the E1 and SN1 reactions compete. And generally, a mixture of E1 and SN1 products are observed. If you want to get more SN1 products, These are favored if a strong nucleophile is present at low temperatures, with low temperatures being the key point here. By the same token, E1 products are observed if you have no or very weak nucleophiles and run at high temperatures. Now you may say, why does the nucleophile strength matter? It doesn't really. The key point is if you want elimination to occur, you need to have something that functionally is non-nucleophilic, or at least such a terrible nucleophile that it's not going to react heavily as a nucleophile. So if you want elimination, you need to run the reaction under conditions where you pretty much have no viable nucleophile present, and you need to run it at high temperatures. If you want substitution, you need to have your nucleophile, or you need to have something that's nucleophilic enough for substitution to occur, and you need to run it at low temperatures. So let's try to predict the product of the following reactions. I'll do the first one, and this really drives home the point. Here we have sulfuric acid, and we're heating this alcohol under acidic conditions at high temperatures. So because we're under high temperatures, and this is a bad nucleophile, we really don't have anything that's nucleophilic. We pretty much, rather than saying bad nucleophile, we pretty much have no nucleophile. We're primarily going to see E1. So in this case, we're going to protonate our alcohol. That in turn generates this great leaving group that will then leave. And from here, another equivalent of our starting material can facilitate this elimination. And that in turn gives us our more substituted alkene elimination product. By comparison, if we take this alkyl halide and we're treating it with silver plus and methanol, we are dealing with primarily low temperatures, and we have a nucleophile that looks like a nucleophile. So we're primarily going to see SN1. So in this case, in the first step, we lose our leaving group. For those curious what the silver does, it activates the halogen because you make a silver chloride salt. Once you have this carbocation, your carbocation can either be attacked by the nucleophile, in which case you would observe this substitution product, or your carbocation could be subject to elimination as methanol, or in this case, ethanol, pulls off that hydrogen, and we get the E1 product. So the SN1 product is going to be major because we're at low temperatures, but we will see some E1 product. So SN1 and E1 reactions compete with one another, and as such, you always need to be careful and cognizant of the reaction conditions. Let's talk next about the regioselectivity of the E1 reaction and some side reactions. The E isomer and the most substituted alkene are favored for the E1 reaction, but mixtures of products are unavoidable. As we can see through this following reaction. The most substituted alkene products are going to be major, but you get a mixture of E1 and SN1 products. Now, when we take a look at cyclic systems, the E1 reaction is only regioselective, favoring the most substituted alkene. In contrast to the E2 reaction, the E1 reaction does not have any conformational requirements. So for example, under E2 conditions, you will eliminate the trans-diaxial hydrogen and get the following alkene product. By comparison, under E1 conditions, elimination will occur in order to generate the most substituted alkene as the major product. One of the consequences of this is that the E1 reaction can be used to, with a minor amount of selectivity, generate the most substituted alkene. One thing I would also like you to note for the E1 reaction, we still get a mixture. So the E1 reaction is not as selective and not at all specific compared to the E2 reaction. As we've seen in this above example, in some cases, different regioisomers are observed for the E1 and E2 reaction. Okay. Again, as we go through a carbocation, the E1 reaction suffers from carbocation rearrangements. This is how you can end up with an alkene at a place that's, at first glance, unexpected in your after elimination. To show you what's happening here in this case, even though we're under typical elimination conditions, your alcohol gets protonated. We in turn generate this great leaving group in the form of water. The leaving group leaves. And this is where, once we have a carbocation, things start to become a little bit chaotic. In that, we can observe a hydride shift to generate the most stable or more stable carbocation. And then from here, we can get elimination to generate the most substituted alkene. So just like in the SN1 reaction, because the E1 reaction goes through a carbocation, we can observe carbocation rearrangements such as hydride and alkyl shifts. So with that above example in mind, I'd like you to take a moment and predict the major products of the following E1 reaction and draw a mechanism for that reaction. So take a few moments, pause the video and work through this example, and then we'll discuss momentarily. So first and foremost, we are going to protonate the alcohol. From here, now that we've generated a good leaving group, the leaving group will leave. And this is where, again, we see carbocation rearrangements. This time we have an alkyl shift to generate a more stable tertiary carbocation. And from here, we get elimination to generate the most substituted alkene product. So again, anytime you have a carbocation intermediate, you need to be wary of carbocation rearrangements. Okay, let's provide a summary now. So here's a full summary of substitution and elimination reactions. and what conditions favor substitution and elimination reactions. In terms of predicting SN1 versus SN2 and E1 versus E2, I like to follow this protocol. First, I check the substrate. If the substrate's primary, you're dealing with an SN2 reaction. If it's secondary, you need more information. If it's allylic or benzylic, SN1 and E1 are favored. And if the substrate's tertiary, you have a choice between SN1, E1, and E2. Next, you identify the nucleophile. Is the nucleophile strong or weak? And is there a strong base present? If the nucleophile is good, you'll see an SN2 reaction. If the nucleophile is a strong base, E2 reactions are favored. Here's a table of common nucleophiles and whether they favor substitution or elimination. If the nucleophile is a weak base and a weak nucleophile, you're dealing with SN1 and E1 primarily. Finally, if you have a choice between substitution or elimination, check the temperature. Is it high or low? High temperatures favor elimination, low temperatures favor substitution. By the same token, in terms of solvent, polar protic solvents favor E1 and SN1, while polar aprotic solvents favor E2 and SN2 conditions. It takes some practice looking at sets of reaction conditions to differentiate between SN1, SN2, E1, and E2. So let's practice that. So if you'd like to convert this into a flowchart, we look at the substrate, the nucleophile, the base, the solvent, and the temperature. So first I ask, is the substrate primary, secondary, tertiary, allylic, or benzylic? Then you check the nucleophile strength. Then you check the base strength. Then you check the nucleophile strength once again. There are many methods of sorting substitution and elimination reactions. You can find whatever table or flowchart works best for you. Let's try to apply what we've learned, and let's try to predict the product of the following reaction. And is SN1, SN2, E1, or E2 the major reaction pathway? So pause the video, take a few moments, and then we'll discuss. So in this case, we have a secondary substrate, ambiguous. We have a good nucleophile that is a weak base, and we have a polar aprotic solvent. So this is all telling me that substitution and SN2 is preferred because we have a good nucleophile. The base is weak, so we can't see elimination really. And we have a polar aprotic solvent, so that favors SN2 versus SN1. So we're going to get substitution and displacement with inversion of our stereocenter. So again, you check the substrate, it's secondary, so we need more information. We have a good nucleophile that's a weak base, which favors substitution over elimination. And we have a polar aprotic solvent, which favors SN2 over SN1. Let's do some more examples. Let's practice predicting substitution versus elimination and identifying the major reaction pathway. So let's try to predict the product of the following reaction and draw a mechanism for this reaction. So pause the video, work through this example, and then we'll discuss. So first and foremost, we have a benzylic substrate that's secondary. Benzylic tells us we're primarily going to see SN1 or E1. We are working under low temp, at least we're not working under high temperatures, and we have something that could be called a nucleophile. So this tells us that SN1 is going to be the major pathway, with E1 being a minor concomitant pathway. So per that mechanism, we're going to lose our leaving group to make a benzylic carbocation. The nucleophile will then attack. That in turn generates a substitution product. From here, we just have a cleanup step and we get our final product. Note, because we go through a carbocation, we get a mixture of stereoisomers. In this case, a mixture of enantiomers. So, whenever you're dealing with a carbocation-based mechanism, you will often see a mixture of stereoisomers, which usually means a mixture of enantiomers. Let's do some more practice. So, given the following reaction conditions, I'd like you to draw a mechanism for this reaction and identify the major reaction pathway. So, pause the video once again, and then we will discuss. So, here we have a secondary substrate, but when you have a highly substituted tertiary carbon adjacent to your secondary carbon, that makes your secondary carbon hindered. And the reason that's important is anytime you have a lot of steric congestion adjacent to your carbon center, it makes it very hard for you to see substitution. Here we have high temperatures and we have a strong base. So this suggests we're going to see primarily elimination. Unfortunately, in this case, because we're at high temperatures and strong base, this favors E2. You can also tell by the fact that we have a polar aprotic solvent. And this means we're going to have to do a little bit more analysis than usual to predict the product. So drawing out a Newman projection, because we need to make sure that the bromine and hydrogen are in the anti-periplanar arrangement. Everything with a wedge ends up on the right. Everything with a dash ends up on the left. That should be a hydrogen because the hydrogen's wedged. So the methyl and hydrogen are on the same side. The bromine and hydrogen are on the same side. Okay. One moment. Okay, let me just redraw that really quickly. Okay, so now we have our Newman projection. Now what we're going to do is we're going to set it up so that the bromine and this hydrogen are set up anti-periplanar to one another. So I'm going to rotate this carbon-carbon bond 120 degrees. So if we have the bromine, hydrogen, and methyl group in the back, we're now going to have in the front the hydrogen, the methyl group, and the ethyl group. So now that the bromine and hydrogen are anti-periplanar to one another, we can perform the E2 reaction. As we can see, post-elimination, the methyl group and hydrogen are cis to one another, and the ethyl and methyl groups are cis to one another. So we get the following product as a single product. So key thing, once you identified that this is in fact an E2 reaction, you need to make sure that the hydrogen and leaving group are arranged in an anti-periplanar rearrangement. This can be visualized by drawing a Newman projection and rotating your carbon-carbon bond so the hydrogen and leaving group are anti-periplanar to one another. Let's do some more practice. So let's take a look at this next reaction. And I'd like you to tell me what's the product from this reaction and draw a mechanism for this reaction. So pause the video, work through this example, and then we'll discuss. So in this case, we have a secondary substrate. We have high temperatures and a strong base, and we have a polar aprotic solvent. This suggests an E2 reaction. The E2 reaction occurs with elimination of the transdiaxial hydrogen, which is the following hydrogen, and that in turn would yield the following product with regioselectivity and regiospecificity. Let's do another example. So here we have the following reaction conditions, and I'd like you to indicate the major reaction pathway and draw a mechanism for that reaction pathway. So pause the video, work through this example, and then we'll discuss. So in this case, we have a tertiary substrate. We're dealing with high temperatures So we have a tertiary substrate at high temperatures, and that suggests we're likely going to be dealing with some sort of elimination reaction. And in terms of elimination reactions, because we're working under acidic conditions, this suggests we're primarily going to observe the E1 product with a small amount of SN1. So to this end, we are going to protonate our alcohol to activate it as a leaving group. From here, the leaving group leaves. From here, then, we get elimination. In this case, the regioselectivity favors elimination to generate the most substituted alkene product, which would be the following alkene product. You will also see as a minor product a little bit of substitution with water serving as the nucleophile, but this is relatively minor, in part because the product from the substitution reaction can readily just undergo elimination. So with that, we've completed our discussion of substitution and elimination reactions and classifying substitution and elimination reactions. Let's do some more advanced examples on identifying substitution and elimination reactions. And for these next examples, you're going to need to pay special attention to the reagents involved. So take a look at the following reaction, pause the video and work through this example, and then we'll discuss. So in this case, we have a tertiary substrate, we have strong base, and we're dealing with high temperatures. Tert butoxide is also a bulky base. So that means although we're going to see E2 as the primary reaction pathway, we have to be pretty careful because this is a special type of E2. The reason why I say that is that elimination is going to occur via abstraction, deprotonation of the most accessible, least hindered hydrogen that's anti-planar to the leaving group. That means that although we're working under an E2 mechanism, we observe the least substituted exocyclic alkene. So remember, when you're dealing with reactions, E2 reactions involving a strong base, please check to make sure that the base is not bulky. If the base is bulky, you're going to see E2 reaction pathways, but you're going to get the least substituted exocyclic alkene. Let's do another example. So here in this case, we have the following reaction conditions. Pause the video, work through this example, and then we'll discuss. So in this case, we have an adjacent, highly substituted tertiary carbon adjacent to our secondary carbon center. This is known as a neopentyl group, and it means that this carbon is very hindered, which means any attempt at an SN2 reaction would be incredibly slow. Given that we have a weak nucleophile and we have an activating reagent, which helps facilitate carbocation formation, we're primarily going to see an SN1 reaction pathway. Again, be very careful when you go through a carbocation, because that's usually a signpost that you may see rearrangements. So in this case, after loss of our leaving group to generate a carbocation, this substrate is not just going to react. You're going to see a hydride shift to generate the more stable carbocation. And from here, your new, more stable tertiary carbocation is going to react via substitution to generate this pretty interesting substitution product. Whoops, the nucleophile just has one carbon in this case. Sorry about that. From here, we're going to pull off a proton as a cleanup step, and that yields our pretty unique substitution product. You will also see as a minor product the elimination product. So, key thing, be on the lookout for neopentyl groups and other groups adding hindrance to your carbon. If you go through a carbocation, such as an SN1 or E1 reaction, be wary of carbocation rearrangements. With that, we've completed this full chapter discussing substitution and elimination reactions. We will continue on with the Chem 112 lecture series, moving on to chapter 10, which focuses on spectroscopy.